In the chemical kinetics lab, we are going to take a look at the Arrhenius equation and determine the activation energy for a reaction. So this is a good review of the kinetics and Arrhenius here at the end of the semester. So what you're going to do is you're going to take a thiosulfate solution and you're going to react it with an acid, and you're going to see how long that reaction takes. The way that you're going to see how long that reaction takes is that you are going to take an index card that has a black X on it, and you're going to mix your solutions as instructed, and then you're going to put your beaker over the index card with the black X, and you're going to determine how long it takes for the X to no longer be visible. You will need to heat up some solutions because we need different temperatures to work with the Arrhenius equation. So your lab handout calls for 30, 40, 50, and 60. Your solutions do not have to be exactly those temperatures. You can do one at room temperature, which is probably around 23 to 25 degrees, and then do 3 at warmer temperatures, as long as they're roughly 10 degrees apart. If they're a little more than that, that's okay, but you don't want to let your solution get to boiling. So, you do need to record those temperatures, and then what we're going to do is we're going to make a plot of time versus temperature. And more specifically, we're going to make a plot of natural log of 1 over time versus 1 over temperature in Kelvin, because once we do that, we can use the slope of that plot to get our reaction. So you're going to make a plot of the natural log of 1 over time, which is the amount of time that it took for your solution to turn dark enough that you couldn't see the X through the beaker. So 1 over T, 1 over the temperature in Kelvin, is going to be your X. 1 over the natural log of 1 over time is your Y. And then negative EA over R is your slope. And the natural log of A, which is your collision frequency factor, is your B, which is your y-intercept. So ideally, B should equal 0, but we're not working under ideal conditions. We're working in real-world conditions, so it's probably not going to be exactly 0, but your y-intercept should be fairly close to 0. So once you get the slope of your graph, you know that the slope of your graph is negative EA over R. So to get EA, what you're going to do is you're going to take the slope of your graph times the negative of R, and that will give you what your activation energy is. Just remember, you will need to convert to kilojoules. So M is your slope. Since we need the negative of R, we're going to take negative 8.314 joules per Kelvin times mole, and then we're going to convert to kilojoules, which I'm sure you are familiar with at this point in the semester. So, how are we going to make our graph? So to give you a little bit of review on how we make the graph in Excel, in column A, we're going to record our temperature in degrees Celsius, and I'm going to abbreviate that as temp. I want to superscript that because that's supposed to be degrees. And then temperature, I need 1 over, Actually, let's do temperature in Kelvin and then we'll convert to 1 over Kelvin. That way we don't have as many steps to do in each of our columns. So then you're going to record the time, which is in seconds, 1 over time, which is going to be in inverse seconds, and then you're going to take the natural log of 1 over time divided by time. So I'm going to make these columns a little bit wider. So for the purposes of doing this demonstration, I'm just going to pick the temperatures in the lab handout. You will need to record your actual temperatures here. So keep in mind that these are not the actual temperatures. These are just the numbers that I'm going to fill in just so that I can get a graph so that we can see what we need to do. So I put in my my temperature in Celsius, and then we know that to convert to Kelvin, we take Celsius plus 273. So I'm going to select the first column and type in that number plus 273. Now, I don't need to keep typing this. What I'm going to do is get this skinny little plus sign up and then just drag this. Now, the next column, I want 1 over Kelvin. So I'm going to take 1 divided by what I calculated in the previous column, and that's going to give me my 1 over Kelvin temperature. So I'm now going to drag that down. And then what I'm going to do is I'm just going to make up some random times. So let's see. So let's say that when it was 30 degrees, it took me, we'll say 85 seconds for that to turn opaque. And then, so keep in mind, I'm making these up. I'm just using this as an example. You will need to record your own temperatures in your own times. So then let's say at 40 degrees Celsius, it only took 30 seconds. And then at 50 degrees, it only took about 20 seconds. And then by the time we got to 60 degrees, it only took 10 seconds. So, now I'm going to do 1 over time again. Oops, need to make this equation. So equals 1 divided by, and I'm going to select the cell that has the time in it. Then I'm going to bring up my skinny plus sign and bring that down. My last step, I need to take the natural log of this value. So once I do that and drag that down, I want to make a plot of 1 over Kelvin versus 1 over time. So I'm going to go to Insert, and under the chart section here, I'm going to select Scatter Plots, and I'm going to do the trend line. Sorry, I'm just going to do the plots. I'm not going to put a line there yet. So under Quick Layout, I'm going to select the one that has a chart title. You will need to label your axes and your chart. I also want this to intersect at the bottom and not at the top. So I'm going to change the axis value where it crosses. Looks like my lowest value there is -5. So I'm going to do that, which moves that to the bottom. So you're going to put in a title. I'm just going to put, let's see, which lab are we doing here? Chemical Kinetics. So I'm just going to put Chemical Kinetics. You will come up with your own chart title. So my bottom axis, my x-axis, is the natural log of 1 over time. So I'm going to fill that in, and my x-axis is 1 over Kelvin, so I'm going to put that in. So the next thing that I need to do is I need to add a trend line. So I'm going to select one of the points and right click on it, and I'm going to bring up a trend line. So we know that our trend line is not always perfect. Hopefully it is fairly close to most of the points, which would indicate that our line gives us a fairly decent representation of what the activation energy is. If our points are too far from the line, we're not going to get a good estimation. So I'm going to scroll down on the Format Trend Line menu, and I'm going to select Display Equation and Display R Squared. So my R squared for my made up data here is 0.9752, which is not too bad. You want your R squared as close to 1 as possible, but it's not always going to be, in fact, it's really going to be exactly 1. So, we got a pretty good R squared value. If we had something like 0.5 or 0.3, then this would tell us our activation energy, our estimation for that is not going to be very good, because our data is too far away from the line for us to get a trend line that gives us a very good approximation. So we're going to take our slope here, and then as I mentioned, we're going to multiply by the negative of R, and then we're going to convert that to kilojoules, and we will have our activation energy for this reaction. So you're going to record your slope and your activation energy on your report sheet, and then you will put that in your lab notebook. So this is our last lab. So this is the chemical kinetics lab. So make sure that you have submitted your purpose and procedure on Canvas, and I will see you in lab.